The capital of France is Paris. You typed a few words, a machine finished them for you, and the whole thing felt like nothing. But look at that big empty gap in the middle. Between your words going in on the left and that one word coming out on the right, something real happened. We just don't get to see it. So what is actually going on inside that box? That box is a large language model, and this entire course is about what lives inside it. Here is what I want to do in the next few minutes. I'm going to draw the whole machine for you, once from end to end, as a single picture. You will not understand every part today, and that is completely fine. Each part gets its own episode later, where we slow down and open it up. By the end of today, you'll feel the shape of the whole thing, and you'll know exactly what we are taking apart next. Let me give you the one idea this whole course rests on, because everything else hangs off it. A language model does exactly one thing. It predicts the next word. That's the entire job. You hand it some text and it asks itself a single question over and over. Given everything so far, what word comes next? For the capital of France is, it weighs everything it has ever learned and decides that Paris is far more likely than London, or cheese, or a comma. The first time this clicked for me, I honestly didn't believe the whole thing could be that simple. Then it does something simple that turns that one trick into everything. It sticks the predicted word onto the end of your text and feeds the whole slightly longer sentence back in as if you had typed it yourself. Now it predicts the next word again, then again, one word at a time until it decides the answer is finished. So everything you have ever watched a model do, from answering a question to writing a whole page of code, is this same little move on repeat. Predict a word, add it on, feed it back, and predict again. That loop right there is the whole engine. So let's actually walk through the box, left to right, and meet every part in order. The first thing that happens is that the model chops your text into pieces. It doesn't read whole words the way you and I do. Instead, it breaks your text into chunks called tokens. Sometimes a token is a full word, and sometimes it's just a fragment of one, like straw and berry split apart. That little detail sounds boring, but it quietly causes some genuinely strange behavior that we'll dig into soon. For now, just picture your sentence cut into a neat row of tiles, where each tile is one token. Now the model runs straight into a wall. It can't do arithmetic on the word France, it can only do arithmetic on numbers. So every token gets turned into a long list of numbers, and the easiest way to picture that list is as a single point on a big map. Words that mean similar things end up sitting near each other on that map. So France and Paris land close together, while a word like cheese sits off in a totally different neighborhood. That is how the model writes down meaning as position, and those lists of numbers are called embeddings. By this point, your sentence isn't words anymore, it's a little constellation of points floating on a map. Now we reach the middle of the machine, and this is where the real work happens. On their own, those points still don't know anything about each other. So the word it has no idea what it's pointing at, and the word bank can't tell if we mean a river or a place that holds money. To fix that, the model runs a step where every word gets to look at every other word and pull in the context it needs. That looking around step is called attention, and it's the idea that made these models possible in the first place. One word asks what it needs to know, the other words answer, and the important ones get pulled in close. It's the part I was most excited to understand myself, and it gets a whole episode of its own. But one pass of attention isn't enough, so the model does it again and again. It stacks the very same step dozens of times, one layer on top of the last. Low down in that stack, a word only picks up the obvious things, like the word sitting right before it. Higher up, it's combining all of that into real meaning, like who did what to whom. By the time your words reach the top, the model has a genuinely rich sense of what your sentence is saying. Now we're at the far right of the machine, the part that finally commits to an answer. The model takes all that built up understanding and turns it into a score for every single word it knows. Picture a long row of bars, one bar for each possible next word, where a taller bar means the model thinks that word is more likely. For our sentence, Paris is a skyscraper, and almost every other word is lying flat on the floor. That whole spread of scores has a name. It's called a probability distribution. Think of it as the model's honest opinion about what should come next. Then the model picks a word out of that spread, usually one of the likely ones, and that's the token that finally pops out on the right. And here is the part that ties the entire machine together. That new word gets added onto your sentence. The whole thing loops back around to the left, and the machine runs from start to finish all over again. So the picture you are staring at doesn't run just once. It runs once for every single word, looping quietly until the answer is done. So let's step all the way back and take in the whole thing at once. Your words come in on the left, get cut into tokens, turn into points on a map, climb up through the stack where they study each other, and drop out the right side as one predicted word, which loops straight back around. That single continuous picture, start to finish, is a large language model. And now I'm going to number the boxes. Each numbered stage on this map is one episode of this course, so you're actually looking at the road ahead. We'll open the tokenizer first, then the map of meaning, then attention, then the full stack, and later how the whole thing gets trained and why it sometimes sounds so confident while being flat wrong. So let's answer the question we opened with. What is actually happening between your words going in and the next word coming out? Your text gets cut into tokens. Those tokens turn into points on a map. The points climb a stack of layers where every word gathers its context, and all of that gets squeezed down into a single best guess. That's the entire machine. And underneath all of it, it's just next token prediction running over and over. Now, that very first step hides more trouble than you'd ever expect. The exact way a model cuts your text into tokens is the reason it can trip over a word as simple as strawberry. So next time we open the very first box, the tokenizer, and watch how this quiet little step ends up shaping everything that comes after it. That's where our machine really begins. Ask one of these models how many times the letter R shows up in the word strawberry. There's a good chance it says 2. The real answer is 3. This is a machine that can write you an essay or debug your code, and it just miscounted the letters in a word a child can spell. That's not a bug somebody forgot to fix, and by the end of this you'll see it was almost guaranteed from the very first step. The reason lives in something that happens to your text before the model does any thinking at all. Before a model sees a single word, that word gets chopped into pieces, and those pieces are called tokens. So here is the question I want to answer by the end. Why does a model that can write essays fail to count the letters in a word like strawberry? The answer is the very first thing that happens to your text, and once you see it, a whole pile of strange behavior suddenly makes sense. Let's go back to the machine we drew in the first episode. Text goes in one end, and the model predicts the next token out the other. But there's a step right at the mouth of that machine before anything else happens, and that's the step we are opening up today. Because here is the thing that trips everyone up. The model never actually sees your letters, and it doesn't even see your words. When you type a sentence, the first thing that happens is that it gets cut into pieces. Take "I love strawberry cake." You read that as a few words made of letters. The model gets handed a short row of chunks instead, and each chunk is a token. A token is just a piece of text that the model has agreed to treat as one single unit. Like a puzzle tile, it can't break down any further. Before we see how those pieces get chosen, let's understand why the model chops text up at all. You might think the obvious move is to give every whole word its own token. But there are millions of words, plus names, plus typos, plus every new word people keep inventing, so that list would never stop growing. And the moment someone typed a word that wasn't on the list, the model would have no way to represent it at all. The opposite idea is to use single letters as your pieces, so you only ever need a few dozen of them. That fixes the never-ending list problem, but now even a short sentence turns into a huge string of tiny fragments. The model has to do far more work to read the same text, and it has to rebuild every word from its letters every single time. So both extremes fall apart, one for having too many pieces and one for having too few. The answer sits right in the middle, and it's the whole idea behind tokens. Keep the common words whole because they come up constantly and break the rare words down into smaller reusable parts. A word like the is so common it earns its own token, while a rare word gets stitched together from a handful of pieces. That way, the list stays a manageable size, usually somewhere in the tens of thousands of pieces, and no word is ever impossible to spell out. So who decides that berry is a chunk, but some random jumble of letters isn't? There's a little procedure that runs once before the model is ever trained, and it builds the whole list of allowed pieces from scratch. It's called byte pair encoding, and I'll run it on a tiny handful of words so you can watch it happen. We start at the very bottom with nothing but single characters. Every word is just a row of letters, and the only pieces we know so far are the letters themselves. Now the procedure does one simple thing over and over. It looks across all the words and finds the pair of neighbors that shows up most often. In our little corpus, E followed by S keeps turning up in newest and in widest. So that pair wins this round. And here is the move that matters. It glues that pair into one new piece is and writes it down as a brand new token. From this point on, is a single unit, exactly like a letter was a moment ago. Then it runs the same step again on words that already have the new piece merged in. Next, it might glue is and t into est because that's now the most common pair. Then L and O become low and W become low. Every round it merges the most frequent pair and the list of known tokens gets a little longer. Do this a few thousand times over a mountain of real text and the common chunks bubble up all on their own. Whole common words end up as single tokens, and the rare stuff stays broken into smaller pieces without anyone hand-picking a thing. Now we can finally solve the strawberry mystery, and I want to show you the real thing, not a cartoon. Here's the word strawberry run through an actual tokenizer. It does not come out as 10 letters. It comes out as 3 pieces, straw and berry. That is all the model ever receives, just those 3 chunks, and the individual letters are already gone. So picture what we are actually asking the model to do. We want it to count the R's, but it never sees an R. It sees straw, berry, and the R's are buried inside those chunks where it can't look at them one at a time. Counting letters inside a token is like counting bricks in a wall you're only allowed to see from across the street. It's not that the model is bad at counting, it's that we took the letters away before it ever got started. And it gets even starker than that. When the word shows up in the middle of a sentence, the tokenizer often packs the whole thing into one single token. So a lot of the time, the model sees strawberry as one solid blob with no seams in it at all. Either way, whether it's 3 chunks or 1, the letters were never on the table. Once you know this, a whole pile of weird behavior stops being mysterious. Take a rare word like an unusual place name the model barely saw while it was training. A common word arrives as one clean token, but this one shatters into 4 or 5 awkward pieces. The model has to reassemble the meaning from fragments, so it's clumsier with rare words than common ones, every single time. Numbers are the same story, and this one catches people off guard. A long number doesn't come in digit by digit like you'd hope. It gets chopped into oddly sized groups. So a long number might arrive as one chunk of digits, then a shorter one, then another, split in places that make no sense. The model never sees clean place values, and that's a big part of why arithmetic can quietly go sideways on it. Here is my favorite one because it feels almost unfair. The same word with a space in front of it and without can become 2 completely different tokens. To the model, Strawberry at the start of a line and strawberry after a space aren't the same thing. None of these are separate bugs that somebody needs to go and fix. They are all the same single fact wearing different costumes. The model reads tokens, not text. So let's answer the question we started with. Why does a model that writes essays miscount the letters in strawberry? Because before it read a single thing, we cut the word into set, raw, berry and handed it the pieces instead of the letters. It isn't thinking about spelling at all. It's working with chunks we chose for it long before it ever woke up. This is step 1 of the whole machine. The very first thing that touches your text and everything the model does is built on top of it. But there is still something missing here. Right now, a token is just a chunk of text with a number stuck to it, and a bare number like that means nothing on its own. So next time we take these tokens and turn them into something the model can actually reason with by giving each one a position in a kind of meaning space. That's the step where berry and fruit start to live near each other, and the machine finally begins to understand. Here are 3 words, king, queen and banana. To you, 2 of those belong together and 1 clearly doesn't. But a language model never actually sees the words. It only ever sees numbers, like the ones scribbling in underneath. So how could a machine that does nothing but math have any idea that king and queen are related? That's the puzzle for today. And the answer is one of the prettiest ideas in the whole machine. The trick is to turn meaning into geometry. Here is the question I want to land by the end. How do you take a word and place it so that its position in space actually carries what it means? By the end, you'll watch king and queen end up as neighbors, and you'll see it happen with real numbers from a real model. And once you've seen it, you'll never look at a list of numbers quite the same way again. Let's pick up exactly where we left off. Last episode we took raw text and chopped it into tokens, little chunks of characters, and each token got handed a plain ID number, just its slot in a big list. But think about what that ID number actually tells you. The token for king might sit near the top of that list and queen way down near the bottom. Those IDs are basically shelf numbers. And sitting near the top versus near the bottom says nothing about meaning. Nothing about that ID knows that a king and a queen have anything in common. So a bare ID is a dead end because those numbers were handed out in the order the list got built, not by meaning. What we actually want is a set of numbers for each word that reflects what the word is about. And it turns out a single number could never be enough to pull that off. So instead of 1 number per word, we give each word a whole list of numbers. And here is the move that makes everything click. We treat that list as coordinates. A pair of numbers is just a point on a map. So let's actually draw the map with 2 directions. Say the left-right direction means how alive something is, and the up-down direction means how big it is. Now cat lands over on the living side and low down because it's small. Whale sits on the living side too, but way up high because it's huge. And rock goes over on the not alive side entirely. Now look at what we just did. The position of each word on this map says something real about the word. 2 words that mean similar things end up sitting close together, and 2 words that mean very different things end up far apart. That list of numbers, treated as a point in space, is what we call the word's embedding. The word stopped being a shelf number and became a place. Now, a real model doesn't stop at 2 directions, it uses hundreds of them. We can't draw hundreds of directions, so just picture that same map with far more room to spread out. And when a model learns good embeddings, something lovely happens across that map. Words gather into neighborhoods by meaning entirely on their own. All the animals drift into one clump, the foods collect in another, and words for kings and queens settle into their own corner. Nobody drew those neighborhoods by hand. The model read a mountain of text, noticed which words keep similar company, and placed them to match. And because these really are points in space, we can measure the distance between any two of them. Cat and dog sit a short hop apart because they show up in the same kinds of sentences. Cat and democracy sit a long way off because they almost never do. So closeness on this map is the model's way of saying two words mean similar things. That's the first half of the big idea, meaning turned into distance. But here is the part that genuinely surprised me the first time I saw it, where the word sit is only half the story because the directions between them matter too. Draw an arrow from man to woman and notice how it points a certain way for a certain length. Now draw the arrow from king to queen. It points almost exactly the same way and it runs almost exactly the same length. The step from man to woman and the step from king to queen turned out to be the same move across the map. And that means the relationship going from male to female became an actual direction you can travel along. Which leads to the trick these embeddings are famous for. Start at the point for king, travel along that same arrow, the man to woman direction, and see where you land. You land right next to queen. So you really can do arithmetic on meaning. Take king, subtract man, add woman, and you arrive at queen. That relationship isn't written down in a rulebook anywhere. It's just a direction baked into the space. So that's the second half of the idea. Relationships turned into arrows, and arrows you can add and subtract. And I don't want you to take my word for any of this, so here is the real thing. This is pulled straight from the small model we're training across this course. We picked one word, then asked the model for its nearest neighbors, the closest points to it on the map. Look down the list, and every neighbor makes sense once you see it. They are genuinely related words, the kind that keep similar company in the text. Nobody wrote that list by hand. The model arranged the whole space this way on its own, and we are just reading it back out. So let's answer the question we started with. How does a machine that only does math know that king and queen are related? It gave every word a home in a huge space, and it learned to place related words near each other. It even lined their relationships up as directions you can follow. King and queen ended up as neighbors, and banana ended up clear across town. But there's a catch I have to be honest about, and it sets up everything from here. Each word gets one fixed point, and it's the exact same point every single time. Think about the word bank. It can mean the side of a river or the place that holds your money. Right now, it only gets one spot on the map, no matter which one you mean. The embedding is frozen and it has no idea what sentence it just walked into. So the next job is to let each word update itself based on the words sitting around it. That's the step that reads the context and reshapes a word's meaning on the fly. And that's exactly what we build next. The animal didn't cross the street because it was too tired. You just read that and you knew instantly that it means the animal, not the street. You didn't even think about it. But a language model doesn't see words, it sees numbers, and nothing in the word it tells it which thing it points to. So how does a machine figure out what you understood without trying? That is the exact problem this episode is about, and the answer is a mechanism called attention. Here is the question I want to land by the end. How does the word it reach across a sentence and grab the word it depends on using nothing but numbers? By the end, you'll watch it happen one score at a time inside a real model. And once you see it, the whole reason these models are called transformers is going to click. Let's start with why this is even hard, because the problem is deeper than one tricky sentence. Take a single word on its own, bank. I haven't told you anything else, so you genuinely can't know what I mean. It could be the side of a river, or it could be the place that holds your money. The word by itself is empty, and only the words around it decide which meaning is real. Now remember what we built in the last episode. Every word gets turned into a list of numbers, a point in space, and we call that its embedding. But here is the catch that ruins everything. That embedding is the same every single time, whether I mean the river or the money. The word walks in carrying one fixed set of numbers and it has no idea what sentence it landed in. So the model needs a step that lets each word update itself based on its neighbors. That step is attention, and everything from here is just how it works. Let's go back to our sentence and follow one word, it. Think of it as having a question it needs answered. The question is basically, which word in this sentence am I standing in for? In attention, that question is called the query. It's the thing this word is actively looking for. Now, every other word offers something back, like a little label describing what it is. Animal holds up a label that says roughly, I am a living thing. Street holds up one that says, I am a place. Each of those labels is called a key. So one word is asking a question and all the other words are advertising what they are. And behind each key, every word also carries the actual information it can give away. That payload is called the value. So each word wears three things: a question it's asking, a label saying what it is, and the content it can share. Query, key, value, and every single word has all three at the same time. The whole trick of attention is matching one word's query against everybody's key and pulling in the values that fit. So how does the model decide if a query and a key actually match? It's simpler than you'd think. It just multiplies them together and adds up the result. That gives one number for how well this word's question fits that word's label. A big number means these two are talking about the same thing. Our word, it runs its question past every word and gets one score for each of them. Now we've got a pile of raw scores, but raw scores are awkward to work with. So we push them through a step that does one clean job. It turns the scores into weights that are all positive and that add up to exactly 1. That step is called softmax, and you can think of it as splitting one full unit of attention across all the words. The word that matched best gets the biggest slice, the rest get less, and nothing is wasted. For our sentence, animal walks away with most of the attention and street gets almost none. Here is the payoff, the moment it all comes together. The model takes every word's value and blends them, but weighted by those attention slices. Most of what flows into it comes from animal because that's where the attention went, and that blend becomes a brand new version of it, one that now carries the meaning of the animal. The word walked in empty and context blind, and it walked out knowing what it refers to. That is attention, the whole thing, once for one word. And I don't want you to take my word for any of this, so here is the real thing. This is an actual attention pattern pulled out of a small model we are training across this course. Every row is a word asking its question, every column is a word answering. Look at the row for it, and the brightest square is sitting right under animal. Nobody told the model to do that, it learned it from reading, and we are just reading it back out. Now there's one honest problem with everything I just showed you. A word doesn't only care about one kind of relationship. It wants to know what it refers to, sure, but it might also care about the verb it belongs to or the word right before it. Asking a single question can't capture all of that at once. So the model doesn't run attention once, it runs several copies side by side, and each one is called a head. Each head learns to look for a different kind of connection. One head might specialize in which noun does this word point to. Another might quietly track word order or match verbs to their subjects. They all look at the same sentence at the same time, and then the model stitches their answers together. So instead of one opinion about what matters, every word gets a handful of them, each about a different relationship. Step back for a second, because this is where the whole field turned. Everything I showed you for the word it is happening for every word in the sentence at the same time. Every word asks its question, checks everybody's key, and pulls in the values that matter, all in parallel. That parallel part is why these models train on enormous amounts of text without falling over. And then you stack this step over and over, layer after layer. In the early layers, words pick up the simple local connections, like which words sit together and belong together. By higher layers, they're combining those into real meaning, like who did what to whom. Each layer's output becomes the next layer's input, and understanding builds up gradually. This mechanism, attention stacked into layers, is the T in GPT, the transformer. It's the single idea underneath almost every model you've heard of. So let's answer the question we started with. How does it know what it refers to using nothing but numbers? It asks a question, every other word answers with a label, and the best matches decide what flows in. And watch what happens when I change one word. The animal didn't cross the street because it was too wide. Now it means the street, and the attention swings across on its own because the neighbors changed, and so did the match. Nothing about the word it changed, only what it was allowed to look at. We've watched one mechanism do one job beautifully, but a single attention step isn't a model. Next time we open up one full transformer block and see what wraps around attention to turn it into a thinking layer. That's where the mesh you just saw becomes a machine. Last time, we watched the word it reach across a sentence and figure out that it meant the animal. That felt like the hard part, and honestly, it's the part everybody talks about. But here is something that bothered me when I first learned this. Knowing which word you are pointing at isn't the same as understanding anything. It gathered the right neighbor, sure, but then it just sits there holding a fact it hasn't done anything with. Looking at the right thing and thinking about it are two completely different jobs. So attention, the whole mechanism we spent last episode on, only does half the work. It lets words look at each other, and that's really all it does. It's a lookup. Here is the question I want to land by the end. What does the model wrap around attention to turn that lookup into an actual layer of reasoning? By the end, you'll watch one full block build itself on the page piece by piece, and you'll meet the one part of this machine that the entire rest of the course leans on. Let me start with the thing everything else sits on, because once you see it, the rest falls into place. Picture the sentence entering the model at the bottom of the page. Every word is now a list of numbers, and I want you to imagine those numbers flowing upward like a river. Each word rides its own lane, carrying everything known about it so far. This river has a name that sounds technical but means exactly what it looks like. It's called the residual stream, and it's just the running state of every word as it climbs up through the model. Now here is the rule that makes the whole thing work, and it's simpler than you'd expect. Nothing in the model ever throws the river away and starts over. Every step reads from the stream, does a little work, and then adds its result back onto it. The word keeps everything it already had, plus whatever the new step just figured out. So the stream only grows richer as it rises, and it never gets wiped and rewritten. So let's drop the first real step into the river, and it's one we already know. Partway up, the stream flows into attention, the exact mechanism from last time. Attention reaches into the river, lets every word look at every other word, and works out what each one should be paying attention to. For our sentence, this is the step where it pulls in the meaning of animal. But watch what it does with that answer. It doesn't swap the word it out for the word animal. It writes a small update back onto its lane, a note that says roughly, by the way, I am about the animal now. And that's the move I want you to hold on to. Attention is the step where words share information across the sentence. It reads the stream, mixes the words together, and writes the mix back down onto the same lanes. After it's done, every word is still itself, but now it also carries what it learned from its neighbors. Now the stream flows up into the second step, and this is the part nobody bothered to give a catchy name. So let me hand it one. If attention is the words talking to each other, this next step is each word going off to think on its own. It's called the feed-forward network, and unlike attention, it doesn't mix the words together at all. Each word enters its own private copy of this step alone, and comes back out changed. You'll also see it written as the MLP, which is just an older name for the very same thing. Here's what it's actually for. Attention gathered the right neighbors, but somebody still has to do something with what got gathered. The word it now carries the fact that it's about a tired animal, and this is the step that acts on that. This is where the model leans on everything it soaked up during training, all the patterns and associations baked into its weights. You can think of it as the word asking itself, given what I've gathered, what does this actually imply? A tired animal probably won't cross a street, and the kind of connection that lets a model know that lives right here. And just like everything else, it obeys the reverse rule. The feed-forward step reads each word off the stream, thinks about it privately, and writes its conclusion back onto the same lane. So now we've got two moves stacked on the river, the words share, and then each word thinks. Attention mixes across the sentence, the feed-forward step digests inside each word, and both of them do nothing more than add their result back onto the stream. There is one small piece left, and it's easy to miss, but the block doesn't work without it. As the river flows, the numbers on it can drift, some lanes running hot with huge values, others barely a trickle. If you let that go unchecked, the next step gets a lopsided, messy input and struggles to do its job. So right before each step reads from the stream, the numbers pass through a small gate. That gate recenters and rescales them, so everything arriving is in a calm, even range. This gate is called layer normalization, and its whole job is to keep the stream well behaved. It doesn't add any new meaning, it just tidies the numbers so attention and the feed-forward step both get a clean read. Think of it as steering the river right before each machine dips into it. So let's step back and look at what we built on the river. A gate, then attention, then another gate, then the feed-forward step, and every one of them writes its result back onto the stream. Lasso those pieces together, and you've got one complete transformer block. That's the repeating unit, the single thing the whole model is made of. And here is the part that surprised me most. The model doesn't do anything cleverer than this to get powerful. It just stamps this exact same block over and over, stacked up the river, dozens of them in a real model. The output of one block becomes the input to the next, all of it riding the same stream. Down at the bottom, the blocks catch the obvious stuff, like which word it points to. Higher up, they're combining those into real meaning, who did what, and what it all implies. Same block every time, and yet the understanding on the river gets deeper with every floor it climbs. So let's answer the question we opened with. What turns attention from a lookup into a layer that reasons? On its own, attention only lets words look at each other, and that's exactly where we got stuck. A full block wraps two things around that lookup. A feed-forward step where each word thinks about what it just gathered, and a shared stream that carries everything upward without ever losing it. The words look, then each word thinks, and all of it gets added back onto a river that never forgets. That's a transformer block, and stacked dozens deep, that's the whole model. Everything I drew today is the block close to how it was first sketched in the original design. The remarkable thing is that this basic shape has barely changed in years. But the machine did get faster, and it did learn to handle far longer stretches of text. Next time we take this exact block and watch how it grew from that first sketch into the model you actually use today. Same river, same block, just upgraded piece by piece. This is the drawing we finished last episode, one full transformer block. Here is the part that surprised me when I actually learned it. This same picture is basically what powered the models back in 2019. The model in your pocket today is running almost the exact same block. So if the core barely changed, what on earth got us from there to here? That's the question I want to answer today. The block held still, but the models somehow got faster and far more capable. So the leap has to live in a handful of upgrades bolted onto this same skeleton. By the end, you'll have watched 4 of them get stamped onto this exact drawing. And each one, it turns out, was invented to kill one specific pain. Let's be precise about what stayed the same, because that's the whole premise. Every block still does the 2 jobs we already know. Attention lets the words look at each other and share what matters. Then the MLP takes each word aside and thinks about it on its own. And the residual stream carries everything upward so nothing gets lost. You stack that block dozens of times, and that stack is the model. Now here is the honest picture of the last several years. Nobody threw this away and drew something new. Instead, they kept the skeleton and sharpened it in 4 specific places. So let's take them one at a time, and let's start with the one you can actually feel. Watch how a model actually writes a sentence. It doesn't pour out the whole thing at once. It makes one word, then the next, and every time it adds a word, attention makes it look back over everything it's already written. So by the time it's deep into a long answer, it's rereading the whole thing again for every single word. That's a mountain of repeated work, and you feel it as the model getting slower the longer it talks. Now here is the fix, and it's almost embarrassingly simple once you see it. Remember from the attention episode that every word carries a key and a value. For the words already written, those keys and values never change. So why recompute them when you could just save them the first time and reuse them? That saved file of keys and values is called the KV cache, and the model looks them up instead of redoing the math. The pain it kills is speed, because the model stops redoing the same math for the entire past on every new word. The second upgrade fixes something the attention episode quietly hid from you. Look at these 2 sentences, dog bites man and man bites dog. Same 3 words, completely opposite meaning, and the only difference is the order. But here is the uncomfortable truth about raw attention. On its own, it treats a sentence like a bag of words, with no sense of who came first. So the model has to be told the order somehow, and the old way was to hand each word a position tag at the very bottom. Slot 1, slot 2, slot 3, stapled on before the word even enters the stack. It worked, but it had a wall, because the model only ever learned a fixed number of slots. Push past that wall to a longer text and it simply had no tag to give. The newer idea, called rotary positions, is cleverer, and it lives right inside attention. Instead of stapling a tag on, it gently rotates each word's query and key by an angle that depends on where the word sits. So when 2 words compare, the match already bakes in how far apart they are. Order stops being a sticker on the outside and becomes part of the comparison itself. The pain it kills is a brittle, walled-in sense of position, and it stretches to longer text far more gracefully. The third upgrade is about how much a model can know without becoming impossible to run. Remember that the MLP, the part that thinks about each word on its own, is where a lot of the model's knowledge sits. So the obvious way to make a model know more is to make that MLP bigger. But there's a brutal catch. If you grow one giant MLP, then every single word has to run through all of it and the cost explodes. So here is the trick, and it's a very human one. Instead of one giant generalist, you build a room full of smaller specialists, and each one is called an expert. Then you add a little router at the door whose only job is to look at each word and send it to the right couple of experts. A word visits maybe 2 of them, does its thinking there, and the rest of the room stays switched off. This is called a mixture of experts, and it's a genuinely different way to spend the model size. Now the model can hold a huge amount of total knowledge across all those experts. But any one word only pays for the 2 it actually visited. So the pain it kills is the old trade-off, where more capacity always meant more cost for every word. With experts you get a much bigger model that still runs like a smaller one, word by word. The last upgrade is the one people ask about most, even if they don't know its name. Every model can only look at so much text at once, and that amount is called its context. The old blocks had a small window, so give one a long document, and it literally couldn't see the top by the time it reached the bottom. You felt this whenever a model seemed to forget what you told it a page ago. It wasn't being careless, the words had simply fallen out of the window. Modern models widened that window enormously, so now they can hold whole documents, long conversations, even entire books in view at once. And notice this window didn't widen by magic, it leaned on the upgrades we just met. The rotary positions we saw stretched to longer text without hitting a wall. The KV cache we saw makes reading all that text affordable instead of grinding to a halt. So the pain it kills is forgetfulness, and the fix was standing on the shoulders of the upgrades before it. So step back and look at the drawing now. It's the same block we started with, the same one from 2019, still standing. But it's wearing 4 upgrades and each one showed up to kill one specific pain. Speed, a brittle sense of order, capacity, and a tiny memory. The core was never replaced, it just kept getting sharpened exactly where it hurt. So let's answer the question we opened with. If the transformer block barely changed since 2019, what got us from there to here? Not a new machine, but 4 targeted upgrades to the same one. A cache so it stops repeating itself, rotation so it understands order, experts so it can know more cheaply, and a wide window so it can remember. And that's the honest shape of progress here, sharpening a good idea instead of throwing it away. We've now seen the finished machine, upgrades and all, but we've never watched it learn anything. Next time we actually train one, and you'll see the real loss curve ink itself down the page as the model teaches itself from raw text. That's where this drawing finally comes alive. Somewhere inside one of these models is the plain fact that the capital of France is Paris. It also knows roughly how to finish a limerick and how a loop works in code. But here is the strange part I want you to sit with. Nobody ever sat down and typed any of that in. There's no file of facts inside it, no grammar rulebook, no lesson plan anywhere. So that's the puzzle this episode is about, and it comes down to one word: pre-training. Here is the question I want to land by the end. Nobody taught the model grammar and nobody typed in the facts. So where does everything it knows actually come from? By the end, you'll watch the knowledge appear on a real model with the numbers on screen. And I promise, the answer is simpler and stranger than you'd guess. Let's remember what we've actually built together across this course. We turned text into tokens, turned tokens into vectors, and stacked attention into a tall machine. But all of that was only the shape of the machine, the wiring and the plumbing. Every connection in there has a number sitting on it, a weight, and right now those numbers are pure noise. So the machine can run, but it's an empty machine that knows absolutely nothing. And I don't want you to take my word for that, so watch what happens if I run it right now. This is our actual tiny model, before we've trained it at all, and here is what it writes. That's not a bug, that's just what a machine full of random weights produces. It's a machine with a perfect body and an empty head. So the real question is, how do we fill it? The whole idea is almost embarrassingly simple, so let me walk one step of it slowly. We take a real sentence from a real book and we cover up the next word. Then we ask the empty machine one thing: what word comes next? The model doesn't hand back a single word though. It hands back a probability for every possible token, a whole spread of maybes. Because it's still noise inside, those guesses come out basically random. The right word, Matt, gets about the same tiny chance as something ridiculous like banana. Now we do the one move that makes learning possible. We check the answer. We already know the true next word was Matt because we took this sentence from a real book. So we compare what the model guessed against what actually came next. That gap between its guess and the truth gets boiled down into one number, and that number has a name. We call it the loss, and it's just a score for how wrong the guess was. A big loss means it guessed badly, and a small loss means it was close. Right now, since the model is noise, that loss is high, which is no surprise, and it's actually useful because a high loss tells us how much room there is to improve. Here is the move that everything hinges on, and it's the heart of the whole episode. We ask a question about every single weight in the machine. Did this number push the guess better or worse? Then we nudge each weight a tiny step in the direction that would have made the loss smaller. Not a big jump, just the smallest of steps. And in a big model, that means billions of weights moving at once. So one training step is really just this: guess, measure the miss, and take one small step downhill. Let me give you a picture for what downhill means, because it's the whole thing. Imagine the loss as a landscape where high ground is bad guesses and the low valley is good ones. On every step, the model feels which way the ground slopes down, and it takes one small step that way. Do that enough times and it walks itself down into the valley where its guesses are good. That whole process has a name: gradient descent, and honestly that's all it is. Measure the miss, then step downhill. And this isn't a metaphor I'm asking you to trust, so here is the real thing. This is the actual loss curve from the tiny model we are training for this course. Every tick along the bottom is another step of guess. Measure the miss, step downhill. Watch it come down. It starts high and shaky, it drops fast, and then it settles into a slow crawl. That falling line is the sound of an empty machine slowly getting less wrong. A number falling on a chart is a bit abstract, so let me show you what it actually feels like. Here is what our model writes at 3 points along that same training run. At the very start, it's the noise you already saw, just scrambled characters. Partway down the curve, real words start forming, spelling clicks into place, and punctuation shows up. By the bottom of the curve, it's writing sentences that actually read like the book it learned from. Now, here is what I find genuinely wild about this. Nobody added a spelling rule between those samples, and nobody wrote a grammar module. The exact same loop was running the whole time: guess a token and step downhill. Spelling and grammar just fell out of it because you can't predict real text well without them. The model learned to write by trying to guess what comes next over and over. So step back with me, because this is the answer to the question we opened on. The only thing we ever asked this model to do was guess the next word. We never taught it that Paris is the capital of France. But across millions of sentences that mention Paris, the cheapest way to guess the next word well is to actually store that fact. So it stored it, not because we told it to, but because the fact helped it lose less. That's the whole trick, and it's why these models feel like they know things. Facts, grammar, the shape of an argument, none of it was programmed in by a person. All of it precipitated out of one dumb goal repeated at enormous scale: predict the next token. Our little model only read a few books, so it only picked up a little. The real ones run this same loop across a huge slice of the internet, which is why they seem to know almost everything. So let's answer what we started with. Where does everything the model knows come from if nobody ever taught it? It comes from one move repeated until it sticks: guess the next word, measure the miss, take one small step downhill. Run that on enough text and knowledge doesn't get installed, it precipitates. But there is a catch buried in all of this, and it's a big one. A machine trained only to sound plausible will sometimes sound perfectly plausible and be flat wrong. Next time, we'll see exactly why these models hallucinate, and why that isn't a bug at all. It falls straight out of the same prediction loop you just watched. I asked a model for a source to back up a claim, and it gave me a perfect one. A real sounding author, a real sounding journal, a year, even a page number. So I went to look the paper up, and it wasn't there. The model hadn't found a source, it had invented one, and it sounded completely sure the entire time. So why does a machine make things up and sound just as confident as when it's actually right? We call this hallucination when a model states something false as if it were plain fact. And here is the question I want to land by the end of this episode. When a model makes something up, it sounds exactly as confident as when it's telling the truth. So why can't it tell the difference? By the end, you'll see that this isn't a glitch that slipped into the machine. It's the same machinery you've already watched in this course doing exactly what it was trained to do. Let's start with what the model is really doing when it answers, because it's not what it looks like from the outside. When you read its reply, it feels like it just knows the answer and says it. But that's not what's happening underneath. It never simply hands you a word. Take a plain prompt, something like the capital of Francis. Before the model commits to anything, it looks at every possible next word and gives each one a score. Then it lays those scores out as a spread, where a taller bar means the model rates that word a more likely continuation. For this particular prompt, the picture is easy to read. One bar towers over the whole page, the word Paris, and everything else is almost flat against the floor. Those scores are probabilities, and the full spread always adds up to 1, the same softmark step we saw a few episodes back. So really the model is saying, I'm almost certain the next word is Paris, and I barely believe in anything else. Then it samples from that spread, the tall bar wins, and out comes the answer you read. Hold on to that, because the answer was never a fact the model looked up, it was the winner of a little contest between words. Now here is the part that explains the whole episode, and it takes us straight back to how the model was trained. Think back to the last episode, to what pretraining actually rewards. The model read an enormous amount of text, and its one job was to predict the next word and get scored on whether it matched what really came next. Notice what was never in that job. Nobody ever checked whether the sentence it produced was true. The reward was for sounding like the text it learned from, and truth was never measured on its own. That's worth sitting with for a second, because it sounds almost too simple to matter. So think about what that kind of training actually builds. It builds a machine that's extremely good at producing text that looks like it belongs. Plausible is the target from the first day of training to the last. When the plausible next word and the true next word happen to be the same, you get a correct answer, like Paris. But nothing in the training ever forced those two to be the same word. They line up most of the time, which is exactly why these models are so useful, and most of the time is not always. So let's go back to my fake citation and run the very same machine on a question it doesn't actually know. I asked for the author of one specific study, and the model reached the spot in the sentence where a name has to go. Watch the spread it draws at that spot. There's no towering bar this time. Instead, there's a whole cluster of names, all plausible, all sitting at roughly the same modest height. That happens because plenty of names would fit a sentence like this one, so the model's belief gets spread thin across all of them. And crucially, nothing lifts the real author's name above the crowd, because that fact was never stored in the model to begin with. But the machine still has to pick a next word, since picking a next word is the only thing it knows how to do. So it draws one of the names from that cluster and writes it down. And that right there is the moment a citation gets invented. The name it landed on is a perfectly plausible continuation, so it reads smooth and sure, exactly the way Paris did. It only happens to be false because plausible and true went their separate ways the instant the real fact was missing. Same machine, same steps, same confidence, but one prompt gave a single spike and the other gave a flat little crowd. The model didn't decide to lie to me, it just did the only thing it does, and this time the plausible word wasn't the true one. Here is the thing that trips almost everyone up, and it's the center of the whole idea. When the model gives you Paris and when it gives you that invented author, the last step is identical. Both times it looked at its spread, drew a word from it, and wrote it out with the exact same smooth delivery. The confidence you hear is just how a finished sentence sounds, not a sign that the model verified anything. And this is the key point. So let me put it as plainly as I can. The model has no separate step that stops and asks, is this actually true? There is no truth meter anywhere in the machine. There's only the spread of what's plausible. A tall bar means this word fits well here, and that's a completely different thing from this word is correct. So the model can't flag the wrong answer for you because it never measured wrongness in the first place. From the inside, a confident truth and a confident guess are the very same event. The uncertainty was real back when the bars were a flat crowd. But that uncertainty gets thrown away the moment one word is chosen and written out fluently. So when someone says a model hallucinated, it sounds like a part failed somewhere. But nothing failed. The same machinery that nails Paris is the machinery that invented my citation, and both times it worked exactly as trained. A model that stays fluent even when it's guessing is the natural result of training a thing to sound plausible above all else. Now, this is not where the story ends, and the next few episodes are all about pushing back on this. Later, training can teach a model to grow a bar for "I'm not sure" instead of always committing to the top guess. And you can hand the model a real document to read before it answers, so that a true bar finally has something solid to stand on. Both of those moves shrink the problem a lot, and modern models are much better for them. But neither one erases it, because underneath it's still a machine sampling from what's plausible. So let's answer the question we opened with. Why does a model sound just as sure when it's wrong as when it's right? Because it's doing the very same thing every single time, laying out what's plausible and drawing from it. It was never trained to feel the difference between true and plausible, so it can't show you a difference it never learned. The confident wrong answer and the confident right answer roll off the exact same assembly line. Once you can see that, the fabricated citation stops being spooky and starts being obvious. That's why I told you at the start this isn't a bug. It's simply what a next word predictor does when the true answer isn't sitting at the top of the pile. Next time we start fixing it by taking this raw text predictor and turning it into something that actually tries to help you. That's where a model stops just continuing text and starts behaving like an assistant. I typed a simple question into a model that had just finished training on the internet. I asked it, "What is the capital of France?" It didn't tell me the answer. It wrote back, "What is the capital of Germany? What is the capital of Spain?" It just kept asking more questions, and I hadn't done anything wrong. That model wasn't broken, it was doing exactly what it was built to do. Here is the question I want to land by the end. The raw model finishes your sentence instead of answering your question, so what small extra step flips it into something that actually responds to you? By the end, you'll watch the same prompt go into two models and come out completely different. And the surprising part is how little it takes to get there. Let's back up to what this model actually learned, because it explains everything. A couple of episodes ago, we watched a model pre-train. It read an enormous pile of text and practiced one thing over and over, guess the next word. That's all it ever did, so that's the only skill it has. When you hand it "What is the capital of France?" it doesn't see a request. It sees a piece of text and it asks itself what usually comes after text that looks like this. And out on the open internet, a line like that is very often followed by more quiz questions, not by an answer. So it does the most statistically reasonable thing it can, and it writes another question. To the model, your question was just a prompt to continue, and it continued it perfectly. So the model isn't refusing to help you, and it isn't confused either. It literally doesn't know that a question is something you're supposed to answer, because nobody ever showed it that. It knows a staggering amount about the world, but it has no idea what its job is. And that's the gap we have to close, without throwing away everything it already learned. So how do you teach a text predictor that questions are meant to be answered? You don't rewire it and you don't bolt on new machinery. You just show it what the right behavior looks like, again and again. We sit down and write out a big pile of examples, and each example is a pair. On top is an instruction, something a real person might actually ask. Below it is the kind of answer we wish the model would give. What is the capital of France on top, and the capital of France is Paris underneath. Each of these pairs is a little demonstration of an assistant doing its job well. We gather thousands of them, covering all sorts of requests, questions, summaries, rewrites, explanations. Real people write the good answers, so the model has a genuine example to copy instead of guessing. The instruction sets up the situation, and the answer shows the model how a helpful reply is actually supposed to look. Think of it as a worked example textbook for how to be helpful. Now here is the part that surprised me, and it's the heart of this episode. Training on those demonstrations is the exact same process as pre-training. It's still just predicting the next word, one word at a time. We show the model, the instruction, and the good answer together, and we ask it to predict that answer word by word. When its guess is off, we nudge it, the very same nudge we used all through pre-training. Do that across thousands of demonstrations, and the model slowly soaks up the shape of a helpful reply. Nothing about the machine changed, and no new part got added. Only the text we trained it on changed. Same mechanism, new data. This step has a name, and now that you've seen it, the name is easy. We call it supervised fine-tuning, because this time a person wrote out the right answer for the model to learn from. You'll also hear it called instruction tuning, since we are tuning the model to follow instructions. But underneath the name, it's the same next token prediction you already understand, just pointed at a better pile of text. Let me show you what that does, because the change is bigger than it sounds. Here are two versions of the same small model we've been training across this course. On the left is the raw one, straight out of pre-training. On the right is that same model after a single fine-tuning pass on our demonstrations. They started life as the same weights, so anything different in their answers came from the fine-tuning alone. I'm going to give both of them the identical prompt and just watch. I ask the raw model on the left and it drifts off, continuing the text like before. I ask the tuned model on the right and it stops and it actually answers the question. Same weights to start with, same prompt, and the behavior is night and day. And I want to be honest about what just happened here because it's easy to oversell. The tuned model didn't get smarter and it didn't learn a single new fact about France. All of that knowledge was already sitting inside it from pre-training. All we did was show it through a stack of examples that a question is a cue to answer. Same next token training as always, just aimed at demonstrations of being helpful instead of at the raw internet. This one step is what turns a raw text engine into something you can actually talk to. Almost every assistant you've ever used started with a pass, a lot like this one. It's a surprisingly small amount of training next to pre-training and it changes everything about how the model feels to use. But there's a ceiling here and it's worth seeing clearly before we move on. Our demonstrations only ever show the model one good answer for each instruction. They never show it that one answer is better than another. So, the model learns to produce something reasonable, but it has no real sense of which reasonable reply people actually prefer. So let's answer the question we started with. The raw model finishes your sentence instead of answering, so what flips it? We show it thousands of examples of instructions paired with good answers, and we train on them the same way we always have, by predicting the next word. That's supervised fine-tuning, and it's why a text predictor will stop and actually respond to you. Same machine, same training, different data, and a completely different thing to talk to. But remember that ceiling, we've only ever shown it one good answer at a time. Next time we teach the model to compare two answers and chase the ones people actually like more, using rewards instead of handwritten examples. Fine-tuning taught it to answer, and next we'll teach it which answer to pick. That's how a merely helpful assistant becomes one people actually enjoy talking to, and it's where post-training gets really interesting. Here are two answers a model could give to the very same person. Someone just typed, "I think I failed my exam and I feel terrible." The first answer says, "You should have studied harder." The second says, "That sounds rough, and one exam doesn't decide everything. So let's look at your options." Both are fluent English, and both are things a text predictor could easily produce. So how does a model ever learn to prefer the second one? Last episode, we took a raw text predictor and taught it to act like an assistant by showing it good answers and having it imitate them. That step is called supervised fine-tuning, and it gets you surprisingly far. But imitation has a ceiling, and this episode is about the move that gets us past it. Here's the question I want to land by the end. How do you teach a model something that's much easier to judge than it is to write down, like which of two answers a real person would actually prefer? Put simply, how do you teach a feel for a good answer when nobody can write the rule book for it? By the end, you'll watch a model learn from judgment instead of from imitation. Let me show you exactly where imitation runs out. To teach by demonstration, somebody first has to write down the ideal answer. That works fine when there's a clear right answer, like fixing a bug or formatting a date. But go back to that exam message from a second ago. There just isn't one perfect reply to write down. Being warm, knowing when to give advice, not sounding preachy about it, all of that is easy to recognize and hard to spell out. I know a good answer when I read one, but I'd really struggle to write the single best one from a blank page. And that's the trap. We want to teach a quality we can feel but can't fully describe, and demonstrations need us to describe it first. So showing the model good answers can only take us as far as the answers we are able to write. So we change the question we ask the human. Instead of "write me the perfect answer," we ask something far easier. We show a person two different answers to the same prompt and just ask, which one is better? And that's a question almost anyone can answer in a couple of seconds, even when they couldn't have written either reply themselves. Picking the better of two is easy, and writing the best one from nothing is hard. And that gap is the whole idea. So we take our model, have it generate two answers to a prompt, and a person marks which one they prefer. Then we do it again on another prompt and another thousands of times over. What we end up with is a big stack of small judgments, each one just saying this answer beat that answer. We call this preference data because every single entry is a human preferring one answer over another. Notice we never had to write a perfect answer even once, we only had to pick the better of two. We swapped an impossible writing job for an easy judging job, and the model can learn from either. Now, there is a practical wall in front of us. A human can't sit and judge every answer the model will ever produce, because training needs millions of judgments, not thousands. So we do something clever, and this is the heart of the whole method. We train a second, smaller model whose only job is to imitate the human's choices. We feed it all those comparisons, and it learns to predict which answer a person would prefer. Then, once it's trained, you show it any answer at all and it hands back a single number, a score for how much a human would like it. A high score means people tend to like answers like this, and a low score means people tend to reject them. This scorekeeper has a name. We call it the reward model because the number it gives out is the reward. And here is the shift that makes everything else possible. We've turned a fuzzy human feeling into a number a machine can compute for any answer instantly. The reward model is basically a stand-in for human taste, cheap enough to ask a million times. Now we've got a judge that can score any answer in an instant, so watch what we do with it. We let the assistant write an answer, and we run that answer past the reward model to get its score. If the score is high, we nudge the model to make answers like that one more likely next time. And if the score is low, we nudge it the other way, so answers like that become less likely. That's the whole loop. The model writes, the judge scores, and we lean the model toward the higher scores. We repeat that a million times and the model slowly drifts toward the kind of answers people keep preferring. This training loop has a name too, reinforcement learning, because the model learns from a reward signal instead of from a fixed correct answer. And that reward came from human preferences, so the full mouthful is reinforcement learning from human feedback, which everyone shortens to RLHF. Now notice how different this is from last episode. In supervised fine-tuning, we told the model exactly what to say, word for word. Here, we never tell it what to say at all. We only tell it whether what it said was better or worse, and it works out the rest on its own. So what does all of this actually change about how a model talks? Before this step, the model is a brilliant mimic that will happily match the tone of whatever comes in. Insult it, and it might insult you right back, because that's just a plausible continuation of the text. After this step, that same model tends to stay calm, ask what you need, and admit when it isn't sure. Nobody wrote those manners into a rulebook anywhere. They emerged because across all those comparisons, people kept preferring the calmer and more honest answer. That careful, helpful voice you feel when you use one of these assistants is mostly this: a reward model trained on human preferences, quietly pulling the model toward what people wanted. And I don't want you to just take the before and after on my word, so here is the honest version. This change is too big to show on the tiny model we've been training all course, so for this one I'm running a small open model that went through this kind of post-training against its raw, untuned twin. Same prompt, 2 answers, and you can watch the tone shift in exactly the direction I described. Now I have to be honest about the catch, because it sets up where we go next. The reward model is only a guess at what people want, and it's a guess learned from a limited pile of examples. So the assistant can sometimes find answers that score high with the judge, but that a real person wouldn't actually like. Maybe it quietly learns that longer answers tend to score better, so it starts padding everything out. The model isn't lying to us, it's doing exactly what we rewarded, which just turns out not to be quite what we meant. When a model gains its own reward like that, we call it reward hacking, and it's a real ongoing problem. The trouble is that the model optimizes the score we can measure, not the taste we actually had in mind. Judgment got us further than imitation ever could, but a judge you can fool has limits of its own. So let's answer the question we started with. You stop trying to write the perfect answer, and you let people compare answers instead. You bottle those comparisons into a reward model, and then you nudge the assistant toward the answers that score higher. It learns from judgment, not just imitation, and that's why these models feel helpful and not only fluent. But we just watched a reward model get fooled. So score alone can't be the whole story for hard problems. What if the model could show its work and we rewarded it for getting the answer actually right instead of just sounding right? Next time we open up reasoning models and watch a machine think before it answers. Here is a small problem. A shop has 12 boxes, 8 pens in each, and it sells 30. How many pens are left? I gave that to a small model and told it to answer right away, and it got it wrong. Then I gave the exact same model the exact same problem, changed one thing, and it got it right. I didn't retrain it or make it bigger. I just gave it room to think first. So here is the question I want to land by the end of this episode. Why does forcing a model to show its work before answering make it dramatically smarter when it's the same model either way? Nothing about the weights changed between the wrong answer and the right one. The only difference was that one version got to write down its thinking and the other had to blurt. By the end, you'll see exactly why those steps are worth so much. Let's start with something about these models that sounds boring but explains everything. When the model produces a word, it does a fixed amount of work to produce it. The same amount for an easy word and for a hard word, always the same. Think of it as one quick think per token, and that quick think never gets any longer. It doesn't get to slow down and grind on a tough spot, it just does its one pass and hands you the next word. Now look at what we asked it to do in the cold open. We wanted the answer as the very next word right after the question. But getting that answer needs a few steps. Multiply 12 by 8, then subtract 30. We just told the model to do all of that inside one quick think and squeeze the result into a single token. That's like being handed a multiplication and forced to shout the answer before you're allowed to work it out. You could probably do it in your head for tiny numbers, but not for a problem with 3 or 4 steps stacked up. Sometimes it gets lucky, but on anything with real steps in it, one quick think isn't enough and it falls over. So here is the fix, and it's almost embarrassingly simple. Instead of demanding the answer right away, we let the model write down its steps first. We give it a scratch pad and we let it think out loud before it commits to anything. Watch what happens when it does. First, it writes one line. 12 times 8 is 96. That's a small step, well within one quick think, so it gets it right. Then, and this is the important part, it reads its own line back and writes the next one, 96 minus 30. And it lands on the answer 66. The problem it couldn't do in one leap, it just did in 2 easy hops. Here is the mechanism underneath that, and it's the whole idea of this episode. Every step the model writes gets added to what it reads next. So when it works on line 2, line 1 is now sitting right there in front of it as context. It's not remembering 96 in its head, it can't do that, it's reading 96 back off the page. Each written step becomes a foothold for the step after it, and the hard problem gets climbed one foothold at a time. Now I want to clear up something, because it's easy to think reasoning is some new machine bolted on. It isn't. This is the same next token engine we've had this whole course, predicting one word at a time. Writing a step of reasoning is nothing more than predicting the next words, exactly like writing any other sentence. The only twist is what it's predicting on top of its own thinking fed back in as fresh context. Let me say that the other way around, because it's the thing to remember. The model isn't reasoning in some hidden place we can't see. It's writing its reasoning down as ordinary text and then treating that text as more of the prompt. So a reasoning model is the same predictor you already understand, just running on its own output. Thinking out loud isn't a metaphor here. The thinking literally is the output, and the output literally is the next input. So if any model can do this, what makes a proper reasoning model? It's how we train it, and this connects straight back to the last episode. Remember, we taught models to prefer answers people like by rewarding the ones they picked. Reasoning training does the same shape of thing, but with a cleaner kind of reward. We take problems where we actually know the right answer, like math or code that either runs or doesn't. We let the model try each one many different ways, writing many different chains of steps. Some of those chains stumble into the wrong answer, and some of them land on the right one. Then we simply check the final answer against the truth and keep the attempts that got there. No human has to judge the thinking, we just ask, did it land on the right result, yes or no? And we nudge the model toward the kinds of steps that tend to reach the check mark. Do that across huge piles of checkable problems, and something quietly remarkable happens. The model teaches itself to write longer, more careful chains of steps, because those are what earn the reward. Nobody handwrote the good reasoning for it to copy. It found its own way of thinking that reaches right answers just by being rewarded for reaching them. That's what turns an ordinary predictor into a reasoning model. There is one more lever here, and it's a strange, powerful one. Once a model can reason, you can just let it think for longer. More steps on the scratchpad means more of these quick things spent before it answers, and we call that test time compute. It's compute the model spends while it's answering you, not compute we spend training it. And within reason, the more of it you allow, the harder the problems it can crack. But watch the curve, because it isn't a straight line up forever. At first, letting it think more helps a lot, and the accuracy climbs fast. Then it bends and flattens out, and past a certain point, extra thinking buys you almost nothing. There's a sweet spot, enough room to work the steps without rambling for no reason. So thinking longer is a real dial you can turn, it just has a ceiling like everything else. So let's answer what we started with. Why does the same model get dramatically smarter just by showing its work? Because it only gets one quick thing per word, and a hard answer needs more thinking than one word allows. When it writes its steps first, each step is an easy one, and each finished step becomes context it can read for the next. And it's still the same next token engine the whole way, just feeding on the thinking it wrote a moment ago. The model didn't get smarter, we just stopped forcing it to think in a single leap. And notice we quietly assumed the model writes down one fixed chain of steps. But at every single word, it's actually choosing from many possible next words, and that choice can go different ways. Next time we open up that choice and see why the very same prompt can give you a different answer every time you ask. That's where thinking meets chance. I typed the exact same words into the exact same model twice and I changed nothing. The first time it said the sky is blue. The second time it said the sky is clear. Same prompt, same model, nothing touched between the runs, and two different answers came out. If the model already knows the answer, how does it give me a different one every time I ask? Here's the part that trips almost everyone up. The model's weights are frozen the moment training ends, so the model itself is completely fixed. Give it the same input and it computes the exact same thing every single time down to the last decimal. So the story question for today is simple to ask and surprising to answer. If the model is that predictable, where is the randomness actually coming from? By the end, you'll know exactly where it lives, and you'll know the two dials that control it. Let's go back to what the model actually produces, because this is the whole key. Way back in the first episode, we said language model does one thing. It predicts the next word. But it doesn't predict one word. When I feed in the sky is, the model doesn't hand me a single answer. It hands me a score for every possible next word it knows. Blue gets a high score. Clear gets a decent one. Falling and the limit get smaller ones, and thousands of other words get tiny ones. Those scores get squeezed into clean probabilities, the same softmax step we met back in the attention episode. And the one thing you need to remember is that all of those probabilities add up to exactly one. So think of it as the model spreading one whole unit of belief across every word it could say next. Blue might get the biggest share, clear a smaller share, and the rest split up what's left. That full spread of probabilities is called the distribution, and it is the real output of the model. Now here is the thing I want to nail down before we go any further. That distribution is the deterministic part. Same prompt, same weights, and the model draws the exact same set of bars every single time. The model never once picked a word. It just told us how likely each word is, and then its job was done. So if the model just draws the bars and stops, something else has to actually pick a word. And that something is a completely separate step that runs after the model is finished. That step is called decoding, and it's where our missing answer has been hiding this whole time. The model says how likely each word is, and decoding is what turns that spread of likelihoods into one word on the screen. Two different jobs done by two different things, and only one of them is fixed. The simplest way to decode is to just always grab the tallest bar. Feed in the sky is take the single most likely word and you will get blue every time, no surprises. That's perfectly valid and it's completely predictable, which is exactly why it can feel flat and repetitive. So the more common way is to treat those bars like a weighted roll of the dice. A word with a tall bar is very likely to get picked. A word with a short bar is unlikely but still possible, and we let chance settle it. This is the moment the randomness enters, and notice where it is. It's not in the model, it's in the roll. The bars were identical both times I ran it, but the dice landed on blue once and clear the next. Picking a word by rolling the weighted dice is called sampling. And now we've found the answer to our whole question, but I don't want to just leave it there because you can actually control that roll. The first dial you get is called temperature, and it does something you can watch. Before the dice ever roll, temperature reshapes the bars themselves. Turn the temperature down low, and the tall bars grow taller while the short ones shrink toward nothing. The distribution gets sharp and spiky. Almost all the probability piles onto the single best word. So low temperature means the dice are loaded hard toward the favorite, and you get safe, predictable, almost always the same answer. Now turn the temperature up high and the opposite happens. The bars flatten out. The gap between the likely word and the unlikely word closes, and suddenly the long shot has a real chance. So high temperature means a looser roll, more surprise, more variety, and yes, more nonsense when it goes too far. The model didn't change its mind about anything here. I just squashed or stretched the same bars before the dice touched them, and that alone changed how wild the answer gets. There's a second dial, and it fixes a different problem. Even after temperature, that distribution still has a huge tail of thousands of barely possible words. Each one is tiny on its own, but pile them all together and there is a real chance the dice land on something bizarre. So the second dial just refuses to consider the junk. It sorts the words from most likely to least, walks down the least adding up probability, and stops once it's gathered most of it. Everything past that cutoff is thrown out before the roll, so the dice can only land on words from the top slice. That's called top P, because you are keeping the top words that together cover most of the probability. There's a close cousin called top K that does the same favor a blunter way, by just keeping a fixed number of the top words and dropping the rest. Either way, the point is the same. Trim the tail so a freak word can't sneak through while still leaving room for a few good choices. So temperature decides how bold the roll is, and top P decides which words are even in the running. So let's put it all together on our sentence. I run the sky is 3 times with sampling switched on, and I get the sky is blue, the sky is clear, the sky is the limit. 3 different answers, and the model was frozen solid the entire time. Every one of those words came from the same bars chosen by 3 different rolls of the same weighted dice. And here is the part that actually matters for how you use these things. Temperature and top P are not part of what the model learned. They aren't beliefs inside the model at all, they're knobs sitting on the outside that you set before you ask. Turn them down, and the same prompt gives you the same careful answer every time, which is what you want for facts and code. Turn them up and you get variety and surprise, which is what you want for brainstorming and stories. So let's answer the question we opened with. If the model is completely fixed, where does the different answer come from? It comes from the fact that the model never picks a word at all. It draws the same bars every time, and a separate step rolls the dice across them, shaped by a temperature and a cutoff that you chose, not the model. The mystery from the start was never the model being unsure of itself. It was just the dice, and now you know exactly where they are and how to load them. We've now walked every stage on its own, from a word becoming a token all the way to the dice that pick the next one. But we've never watched all of them run together, in order on a single real prompt. Next time is the capstone, where we take one prompt and trace it slowly through the whole machine, end to end. Every piece you collected across this course, finally in one picture. You type one sentence, you press enter, and a heartbeat later, a word comes back. Across this whole course, we've taken that machine apart, one piece at a time. Tokens, meaning attention, layers, training, the way it picks each word. You've seen every one of those parts on its own now. But you've never watched them all run together, start to finish, on a single real prompt. So that's what we are going to do one last time. Here's the sentence we'll follow the whole way through. The capital of France is. We'll walk it into the machine on the left, past every stage you've learned, and watch a word come out the other side. And this time you will be able to name every box it passes through. Here is the question I want to land by the end. What actually happens in that fraction of a second between pressing enter and getting a word back? Watch it enter on the left, because the very first thing the machine does is cut it up. It doesn't read words the way you do, it reads pieces called tokens. The capital of France gets sliced into a short row of these little chips. This was the tokenizer, and it's where every weird spelling quirk we saw comes from. Each chip is really just a number, an ID pointing to one entry in the model's vocabulary. So right away, your sentence stopped being letters and became a row of numbers. Next, each of those ID numbers gets looked up and turned into a long list of numbers, a point in space. We call that point an embedding, and words with related meanings land near each other on the map. So the geometry itself is carrying the meaning. Right now though, those points are generic, just the plain dictionary sense of each word. They don't yet know they landed in this particular sentence. Fixing that is the next stage, and it's the one that changed the whole field. Now the tokens are finally allowed to look at each other, and this is attention. Every token asks a question, checks all the tokens that came before it, and pulls in the ones that matter. Our last token looks back across the sentence and grabs onto capital and France. That's how is stops being a generic word and starts to mean is in a sentence about the capital of France. This was the mechanism that changed everything. Attention doesn't run on its own, though it sits inside a repeating unit we called a transformer block. Inside that block, a handful of attention heads each look for a different relationship at once. Then a small network does a bit of private thinking on every token. And all of it rides on a stream that carries information straight up the machine. The version running today has upgrades on top of that, the ones that let it hold a long document in mind and run fast. But the shape is the same old sketch, just tuned. Here is the part that's easy to miss, so watch the height of the machine. That block isn't run once. It's stacked dozens of times, one on top of the next. Your sentence flows up through every layer, and at each floor, the meaning gets a little sharper. The low layers catch the obvious links, like which word points to which. The high layers combine those into real understanding, like this is a question about a capital city, and the answer should be a place. By the top floor, that last token has quietly gathered everything it needs to make a guess. And at the very top, the machine finally commits, but not to a single word. It gives a score to every word in its whole vocabulary and softens those scores into probabilities that add up to 1. Paris gets a tall bar, Lyon a short one, London shorter still, and thousands of other words get almost nothing. Now, every number that shaped those bars was learned, not written by a person. The machine read an enormous amount of text and slowly tuned itself to predict what comes next, over and over, which is also exactly why it can be confidently wrong. If the real answer was never in what it read, it doesn't stop and admit that, it just hands you its most plausible guess anyway. There is a reason this feels like talking to a helpful assistant and not a random stretch of the internet. After all that reading, the machine went through a second education. First, it was shown good examples of following instructions, so it learned to answer rather than ramble. Then it was nudged toward the replies that people actually preferred. That's why the tall bar here is a clean, direct Paris instead of a messy web page. And for genuinely hard questions, some models first run this whole loop quietly on a scratchpad before they answer. Our prompt is easy, so it skips that, but the machinery would be exactly the one we've been tracing. So we are standing at the top with a fan of probabilities, and the machine still has to actually choose one. That choice is a separate step called decoding. A careful setting almost always takes the tallest bar, so here it takes Paris. Turn the temperature up and it would sometimes reach for a shorter bar instead, which is why the same prompt can give you different answers. Either way, one token gets picked and it drops out of the machine on the right. Paris, the first word of the answer, but the machine isn't finished because it only ever predicts one token at a time. So watch what it does with the word it just made. It adds Paris onto the end of the sentence, and then it runs the entire machine again from the left. Tokenize, embed, attention, all those layers, a fresh fan of bars, another pick. This time the input is the capital of France is Paris, and now the tallest bar is just a full stop. It picks it, the sentence is complete, and the loop finally comes to rest. So let's answer the question we opened with. What actually happens in that fraction of a second between pressing enter and a word coming back? This happened. The machine cut your sentence into tokens, turned each one into a point in space, let them look at each other through attention, and carried them up through a tall stack of layers. At the top, it weighed every possible next word, picked one, and then looped the whole thing to write the word after that. Every single box in that picture is now something you can name and explain. When we started, this was one mysterious machine that turned your words into its words. Now it's a sequence of plain steps, and there isn't a magic one hiding in the middle anymore. That was the whole point of taking it apart. You came in asking what a language model does, and you are leaving knowing how it does it, one honest mechanism at a time. Thanks for following the whole trace with me all the way to the end.